The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people are evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, the group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everybody, I'm geologist Philip Ong, here with Mr. Dan DuPont from Hawaii Tracker, hawaiitracker.com. Bringing you guys another Kilauea volcano update, and today a little bit more of a Mauna Loa deep dive. Mauna Loa monitoring signals and a little bit more of the background research to help you guys understand maybe what patterns on Mauna Loa might be sourced from. But we'll start off with our Kilauea. We'll go through, touch all our bases on Kilauea, and give you guys a pretty quick eruption update on Kilauea today. And starting off here, this is a view from the KW cam of the USGS Hawaiian Volcano Observatory, showing that lava lake circulating in this 24-hour time-lapse automatically generated by their website. I just have it zoomed in all far in here so you guys can see this active surface area, largely unchanged as it's been for a couple weeks now. With this whole backside of the crater all crusted over, but with lava underneath it to the point where you do occasionally see lava leaking out of some of these gaps around the side of the crater. And so that is the view there from the KW cam. We will show you guys a lava lake is still deepening. Here it is on this latest USGS graph. You can see it's up to, I'll read this for you guys, 226.2 meters. So that's unofficially the depths, 226, which ends up being 741 feet. USGS website still has it at 725 from when they put the update out this morning, when it was a little bit lower still. That's the lava lake still deepening there very slowly. SO2, our most recent measurements, are at 1,000 tons per day. Before that, it was 850, somewhere in that range, right in there. So that's our range. It's been within the variation we've seen within the last few months, in fact, since we dropped off steeply from the beginning of the eruption with lots of gas and lots of lava being erupted out. All right, we'll get through our Kilauea section here by showing you guys deformation data, and then we'll take Kilauea questions first, and then we'll go and turn to Mauna Loa after that. Here's a deformation plot on Kilauea for the last 2 days, tilt. And the scale here is pretty small, minus 0.3 to positive 0.5, less than 1 microradian total, what you see in this 2-day plot right here. So if we scroll down and look at the past week, we can see it in a better scale where we have 1 microradian per hash here. As you can see, we did have a smaller deflation inflation, and also say smaller in context of the previous ones during the last month. And our recent trend is just a little dip and a little dip, so it's really just a part of the background variations that we see. If we scroll down to the last month, we can see that finally our POO line is leveled off at 0, it's flatline, so now we can basically ignore it and focus only on a blue line Ue Kahuna for the summit, where we can see these deeper, we can see this deeper back-to-back deflation, inflation, then a bigger deflation, inflation that we had about a month ago, whereas in the last 2 weeks, we've only had a couple of these small ones. And really, in the last few days, it's been fairly stable and fairly steady up here. Not a lot of change in the tilt there to speak of. That's the USGS HV update. 1,000 tons per day, 225 meters, 739 feet. Shows you guys a graph of how it's a little deeper than that, but obviously it varies up and down on a smaller cycle, larger cycle, and so on and so forth. Right. Otherwise, no real change in information in the East Rift Zone or in a Halemaʻumaʻu observations there. And so here's our Kilauea last 24 hours thermal time lapse. You can see there's a little bit of a lava upwelling, ooze up here on this western edge. And here's our west vent. And you can see that this is our entry point right over here. All right, so lava. I'm going to change my color here. So you see lava's coming out of that spot over here. And we had a little ooze up down here at the bottom. Right, coming out of this west rim of the crack, and that might correspond to this stable higher pressure, because if I am able to zoom in a little more here, let's try. You can also see there's a burst right here where we see lava breaks out from the top of this channel and then it crusts back over again. But it bursts out and it sends a brief little flood here over the edge of this input. Right, and this, you can see, it's coming a little bit more from this direction right in there. It's unclear how that relates. If that's that southern entry that was a little bit more clogged, as opposed to that northeast entry that was an overflow more in this direction. I'm not quite sure in there. It might be that more southern one there that's bursting open a little bit, so showing signs of life there. Can't really tell otherwise underneath the crust over here. And otherwise, you can see that we still have this peninsula that somewhat surrounds the tipped over island that's right in here. So that's all status quo for Kilauea. Here's that last outbreak and ooze up on an S1 camera view. The ooze up is just visible off here on the left, and then we'll burst out overnight right in there. And it does appear to be coming from this angle, more from that original entry point source. And you can see it kind of zips up there, whereas we still have an entry point coming more in this direction as well. So just some minor changes there on the nozzle of Kilauea. So there's a couple photographs here from April 7th, April 8th. You guys can see similar view there. A little bit better what it looks like to the naked eye. Try to pan around here so you guys can get a closer view of all these different areas. That's one. And even more zoomed in here, the west vent down here, our original island, all the terraces, and this area back through here. And there's the entry point right there. Okay, one last one, which is of interest. This is from yesterday, April 8th. And the caption on this one notes that the crusted over southern shoreline of the lava lake in Halemaʻumaʻu at Kilauea summit has accumulated talus rubble blocks on the surface since it solidified in February. On April 8th, HVO field geologists noted steaming east of the talus above the rubble in a photo that was producing hazy viewing conditions. So there's that photo right there. I'm going to go into it a little closer for you guys here. All right, you can see this slide surface on the right side of the photograph here. That's that southern rim, the southern crater edge wall of Halemaʻumaʻu. And you see all this debris, all these blocks, talus or talus, however you say it. I'm not sure if I've said it both ways by now, right? And you can see north of there is this area that's got a lot of gas coming out. Not only there, but there's another spot down here to the south. And if I zoom it back out, you can see that is visible all across, right? So if I go back a couple photographs here, come into this one, you can see a little different view right in there, where that talus slope is, and steaming spots on the sides here, and a few more. Right, this allows us to see that there's some more here in the foreground as well along the southern side. And the difference there is, if I zoom it back out here, you can see that this northern side is much more sulfurous, a lot more yellow color and white color there. So it's not just steam coming out, it's some volcanic gas that's got sulfur and deposit something like a calcium sulfate gypsum, a white mineral, or a yellow sulfur mineral, or a white sulfur mineral, and so on and so forth. You don't see that so much here on the south side. But it's interesting because this is the south side, is where we have seen more of the water features before, when we're following the water pond filling up within a collapse pit of 2018. We often saw water coming more from this side of the caldera, right? So it's interesting to think about whether perhaps if we have heat radiating out, at some lesser rate, perhaps the water is able to get a little bit closer and start steaming a little closer to this lava bowl that's filled with this cooling mush right in there. Yeah, so that's it for Kilauea. Just want to mention here in our first break that there's a lot of other information on Hawaii Tracker we're not going to get to today. We're going to spend more time on Mauna Loa today, but there are other things about Kilauea, including 2018 eruption. There's a post in Hawaii Tracker that Dane put up about earthquake characteristics affected by magma viscosity. Interesting research there. You can check that out there. And also a volcano watch this week. That is what's that seismic noise, that we'll also get into more detail next week there. But if you guys can't wait and want to check it out sooner, you can go to hawaiitracker.com and you guys can read the written versions there ahead of time. So Dane,
yes.
What do we got for Kilauea?
Well, we got a few questions here. I got one question that's going to blow your mind with how difficult it is. Straight away, I'm just going to drop it on you. Can you show where Volcano House is on the edge of the caldera?
Show where it is on one of these maps. Let's see if I can. Yes. All right, so this is that view that's pretty close to that KW cam, that photograph posted by the USGS. And so the Volcano House is actually way up here in this photograph right in there. Let's see if I can zoom in on it.
Enhance.
Yeah, there it is.
Enhance.
And there it is right there. Volcano House.
All right.
Nestled in the
Well, let's get
trees.
it.
Go ahead.
Yeah, we got some other ones here. Sharon asks about the depth of the lake and its characteristics with the ongoing eruption. She asks, as the lake deepens, will it create pressure against the inflow enough to inhibit incoming lava? It's kind of similar to the northern vent that we've talked about previously.
Yeah, I mean, it's hard to really know. I haven't seen any real calculations. It seems intuitively that it does put some pressure back on the vent, right? But that we've seen eruptions with way bigger pressures than this. And so if the eruption pressure is that low, where that's all it takes to fizzle it out or to block it, then something else might do it anyways. right? Some underground deflation, inflation, or something equally small, right? Where so yeah, that could happen. But part of that is because the rates are actually pretty low coming out, and we've seen at Kilauea Iki in 1959 we saw the lava fountain erupt through the lava lake and still fountain up hundreds of meters in the air, right, over 1,000 feet through the lava lake. So if you have enough pressure, then the lava there just doesn't make that big a difference, right? Maybe more so the more it cools and the more it hardens and all of that. It might force a change in a near surface. And lava could come out some different version of the crack, right? That's the nozzle change we've seen by that west vent recently.
Witness Me asks a question that I do have a little experience in. How hard is it to use the lava as a heating source for cooking? Now, there's some interesting dynamics there, right? Because I assume the question's about the hot dogs in Iceland, because that's kind of where it came back up from more recently. Some guys were cooking hot dogs directly on the flow. And USGS didn't think it was the greatest idea in the world, but and they've talked previously about people asking about cooking marshmallows over volcanic vents, and that's a terrible idea. But cooking on lava, or it starts to get a little more interesting. The one that they were in that photo, if I remember correctly, the USGS was upset about. On the marshmallow one, about the gases, right? Obviously coming up. In the one on the hot dogs, it was about pieces of volcanic glass, or little small microscopic, up to even ones you can see. And that was what they were upset about. But I've cooked like Jiffy Pop out on the cooled lava flows without issue. But it's pretty variable, that whole thing. You can make it happen. People have done it long time. It's just there's big time issues if you do it right.
Yeah, for sure. But there's the actual logistics of it, right? As part of it, you're gonna cook not the man, but the actual whatever it is you're trying to cook, and not cook yourself in the process, right? So when it's down in a pit like it is now, that makes it really hard. Then there's the logistics, having to protect it from the gases and the glass is another thing. There's a cultural aspects as well, of course. I gotta bring up that are different everywhere in the world, and it just it's a matter of what the local cultural acceptances are, right? Whether and how and who and where and when you were to do that, because for example, here in Hawaii, some people believe that spirit of Pele is in a lot of lava flows, and you need to make some gesture or offering or something along those lines to make it more appropriate, right? And that said, there are stories of steam vents by Volcano House, in fact, being used to steam nene by Hawaiians a long time ago. So it's it's all, and I'm sure it was all done with respect, so it's not to say that it's not possible, right? But it's all beyond my knowledge at that point, the cultural variations of place to place, especially somewhere like Iceland compared to Hawaii.
Right.
Yeah.
All right. Well, this will make a good transitionary question. Mary asks, how are Kilauea and Mauna Loa connected? Are they completely separate volcano, or is Kilauea kind of a breakout on Mauna Loa slope?
Yeah, so it's Kilauea is built on Mauna Loa slope, and start from the back and go backwards. It did grow through the slope of Mauna Loa, but also through the ocean crust in a separate pathway than Mauna Loa's, and to the point where they're chemically distinct. And for the longest time, that's been the big argument of why Kilauea and Mauna Loa are so definitely separate magma sources. And that's just one part of it, because we've also said that the volcano is, because Kilauea is on the slope of Mauna Loa, on its south slope, essentially. It's essentially on its south flank and interacting with it and piercing through it. And so there could be dynamics there that the volcanoes could interact by actually pushing on each other dynamically, closer to the surface, right? That's certainly possible as well. But we are going to talk today, after we go through our Mauna Loa signals, about a third way that's been model it as a possibility, and that makes it seem really intriguing, and maybe it's hard to say likely, right? But it's something that you have to really got to consider. There's a way that they're connected by pore pressure, without actual mixing of the flow, and being able to respond to either surges in magma that come from a hotspot that hit both volcanoes, as was the case in 2002 to 2007. That's what we're going to focus on at the very end. And as well, when we have changes in lava output from Kilauea, changing how Mauna Loa is behaving during times when you don't have those lava surges. So it's a little bit tangled up there, but it seems like it's been untangled, at least with one possibility of a model that does work.
Yeah. Right. Well, before we get into the Mauna Loa section, I do want to thank everybody that did make donations on HawaiiTracker.com. We are brought to you by HawaiiTracker.com. It is a social media site that's community-based that we share onto as our primary ways of putting up our information. The best way you can support us is to like, subscribe, share this video. We don't have an advertising team to be able to, and the revenue to be able to do that. So we rely on our viewers to help share the message. If you appreciate what Philip and I have been able, are sharing with you, then please consider sharing it. Become a member on HawaiiTracker.com. It's free, easy to do, just like any other social media. And maybe consider making a donation on HawaiiTracker.com/support. I do want to thank Brian B, Mel S, and Barbara R for making donations on the HawaiiTracker.com. And for the next segment, we're going to be talking Mauna Loa. If you have any questions, we'll get to them at the end of that segment. So with that, back to you, Phil.
Holiday, yeah, and please go on HawaiiTracker.com, and even just making an account, like Dan said, is makes a big difference, because that helps us with our advertisers as well. So that's a free thing. That's a little bit extra, but something maybe we can mention one extra time today. All right, so back to Mauna Loa here, and we'll start by looking at the earthquakes on the island. So here's our USGS current earthquakes. We can see that we still have our ongoing Pahala deep earthquake swarm, which is really more of this one's right in here, because if I zoom in more, we have these ones over here where that was a magnitude 4.3 and 3.9 that are part of this Kilauea segment of Mauna Loa, right? So we do have a couple earthquakes down in here. There is one over here, which is interesting. 1.5 is kind of a small one, but we'll look at that area as well, the Kona area. Most of the action has still been here to the northwest of the summit caldera of Mauna Loa, with a few earthquakes in that summit region. And a few, but really not that many. Most of the action is really up here. And that's an area that has flared off before, as we've detailed in past updates in relation to the 75 and 84 eruptions. So there is some important magma pathway that's over here in this area. Right? It seems like a little bit of the earthquakes here span a greater range of depths than you see right by the summit recently anyways, right? So it might be that there's a different magma pathway, and that's probably why you have that source over there. Right, so if we look at the earthquakes as far as the rates, here is the past month on Mauna Loa. You can see that we do still have those earthquakes happening at a rate of 40 per day or so altogether in that summit area, which is a little bit higher in our background we had before. But that had been variable from being maybe in a range of 30 to 40 down to 10 to 20. And then we had that the big peak of it when all of the earthquakes initiated. And it's kind of tailed off. You can kind of see that tailing off version here with maybe a second little pulse coming in. Right, but still fairly low rates, because earthquakes per day were still at 100, and we're nowhere near the consistent background levels of several hundred per day for a long time that would indicate an imminent eruption. Right, an imminent eruption is what we care about as humans on the surface. There can be magma movements inside, and in fact, we'll talk about those things happening without lava coming out of the ground since 1984, in fact, on Mauna Loa. Looking at the last year here, you can see that we are at the highest point that we've been all year. We did peak at over 250 earthquakes per week now as a scale over here. And we're close to that earlier in the year, and we've had other peaks that were close to 200 per week 100 per week background, and so there's still all this sawtooth pattern, this variability, and not this consistent elevated level. But it does seem like it might be growing a little bit and growing a little bit. So it's, as we've said before, maybe building to something, and we'll have to just wait and see what the next move is. And because the pattern is not something that's predictable, it's just something we watch and try to make sense of. Looking back for the past 5 years, you can see that even in the past 5 years, now we're earthquakes per month, changing the scale once again. And per month, we got up to in a range of 700 earthquakes per month for 2 months back to back. And before that, you can see that we were at lower levels there. So maybe building up there, but when we get the buckets this big, you can't really panic because that there's a lot more variability than is being shown here. These are not it's not as constant as it looks in this graph, right? We know that there's gaps, as we saw when we started off with that 1 month plot. So going to Mauna Loa's summit tilt here, just the normal everyday variations on both axes here. For the past week, for the past month, we can see that it looks like there was some change from about +1 microradian to -2.5, 3.5 microradians at the summit of, it's hard to see here, appears to be a deflation, right? So a very small deflation, maybe 3 microradians is the size of our deflation inflation events. So we've seen on Kilauea, the small ones, and we've seen bigger ones in that too. Not to say that this is directly relatable, the position of the station, everything else, and the location of the magma chamber is not all exactly the same. But just give you guys something to refer to as a comparison there. If we go to the GPS, this is the most interesting thing here, is if we look on a cross caldera distance here, this is the past year. This is between the station near the summit of Mauna Loa on the north, and the south pit station in the south here. This is the Chilean local length between them here. And you can see that it's been a steady upwards climb on average with a few dips. There was one back in July 2020. There was one September 2020. There was one in November 2020. And there seems to be happening the biggest one so far, as far as that signal looking that same, began here in late March of 2021. So that's a signal that is the biggest change there. It is showing a contraction across the summit. And we'll talk about what that might mean here shortly. But to put it in context, here's the past 5 years. And so for the past 5 years, you can see that we had a background rate of filling, essentially, of spreading, with a little bit of a flat spot here in 2018. Kind of coincident with the build up to and the 2018 eruption. And then after the 2000 eruption is over, it resumes, and actually resumes at a steeper rate, right, filling faster, as evidenced by spreading of the summit caldera length there, with these occasional little dips, right, that have been possibly associated with movements of magma in and out of the magma chamber and the dike and sill system that's part of that whole Mauna Loa summit reservoir area and all the connectors there. A little bit different than Kilauea, but it does have a lot of those same components. So that is it for the GPS here. It's just worth noting, going down here, looking at just a vertical motion. Our scale here is in meters, so we're looking at 0.01. This is essentially centimeters, 1 centimeter, 2 centimeter, 3 centimeters right there. So you can see that in the last year, we've come up from, call it -2.5 to +2.5, maybe 5 centimeters or so. So that's the net overall, because there have been times where it's gotten higher and then lower, higher, lower, higher, lower, so on and so forth, right? And right now it's going lower again, so this drop is maybe a centimeter or so vertically, within a range of, you can see this one back here might have been 2 centimeters. So it's still ongoing. We'll see how long it goes on and what it looks like here in a few days. But worth noting that the vertical motion is definitely measurable. It's not as drastic as what you see on the north-south, pretty close to north-south distance measurement there. Right, although we got to note the scale here as well. This is right 1 centimeter, half a centimeter, 0, 1.5, 2. So
we have a $50 super chat from Gary Bryan. It says, "Thanks so much for these updates. Great job as always." Mahalo, Gary.
Hello, Gary. All right, so once this has been talked about online, then we can see I was going to bring up here this Twitter exchange that was with USGS Volcanoes, and so user updraft with WMax here is asking about that exact tilt GPS length plot right there, and asking for some guidance in physically interpreting what they call a deflation event at Mauna Loa. I do note it coincides with a shift in earthquake activity from Mauna Loa's summit to its flanks, and that's an interesting thing to note as well, right? And here is their reply, and kind of as they labeled it, where the earthquakes were in that summit region and more in the flank regions, coincident with contraction. They're writing here inflation, deflation. Right, but that may well be inflation and deflation, but we refer to it here. You can see the USGS reply. You're correct that it seems to correlate with a shift in seismicity. Good eye, it's not deflation, but contraction. The cause is unclear. It could be magma cycling from shallow to deep levels, or even a decrease in a magma supply. We're still investigating, so we'll actually look at both those possibilities here. Magma cycling from shallow to deep is something we'll look at in this research as a possibility that's happened before, and decrease in magma supply as another possibility in research as well. Right, so what you can see here is that Dane requests some InSAR of Mauna Loa, and USGS very graciously obliges here and has posted an interferogram on Mauna Loa. So we have that here, issued April 8th. Mauna Loa Summit interferogram, and they've labeled a few things here. It's pretty zoomed into the Mauna Loa Summit caldera here, but you can see this is a summit caldera, Makua Veil here, and that's the south pit right there. And they're noting this overall broad area. I'll change my color so you guys can see it. This overall broad area is an area of summit inflation, broad deformation field from summit inflation. It's labeled there. There's also, if we zoom in a little bit more, there's a smaller feature in here, which they're saying is a little local subsidence spot as due to these earthquakes. These were very shallow earthquakes that occurred here. I have them plotted on their InSAR overlaid as well. All right, so that's all we're really seeing. You don't really see a whole lot. You really can't tell much from the edges of the photograph, although you do see the patterns are pretty convincing as they've labeled them at the summit. We are missing some other information here, but you guys can see that the cycle they're noting is 1.55 centimeters from blue all the way across the purples and yellows to the green again, and it's from November 2020 to March 2021. And so they also note that the fringes coincident with subsidence inside Makua Veil caldera related to a shallow earthquake that was recorded on March 6th. So we believe March 6th is part of that window as well. So the red circles are earthquakes. Recent contraction on a summit has not yet been identified in any interferograms. So a little bit more on this in a second here, but that's not part of this. Most recent signal is not part of this. This is basically showing us this more of a background signal there, right? So background signal there. So you got to make it more clear. Let me zoom in on this a little more here. We have outlined here in yellow, this yellow box here, that period of time that the USGS interferogram is covering. And so cover is this broad, essentially you're moving from here up to this level right here. So we're catching all this growth right in there. And we were missing the contraction event that happens beforehand in October, and we're missing the one that happens here in late March. So
that we have a $10 super chat from Brian Beelman. He says, "Thank you guys," and that is all in the message. Hello, Brian.
Hello, Brian. So Dane follows up with USGS here, and it says, and does show them that ask about the contractions there, and the response is worth noting. The October contraction is hard to see in the InSAR because it's pretty small. It's more likely that the recent contraction will show up in interferograms, but we'll need to wait a few more days for an acquisition. So the satellite only flies by every so often, and that's what we're waiting for, to try to catch this more recent signal. If it becomes a little larger, it seems like it's a larger signal than we've seen thus far. So, and they said we'll see what we can arrange. So we will await that as our next iteration here of this story of what's happening with these small variations and large variations in the summit. But the most recent update here from Mauna Loa, issued yesterday, Thursday, April 8th, does note Mauna Loa is not erupting. Rates of deformation and seismicity at the summit remain slightly elevated and above long-term background levels. Other Mauna Loa monitoring data streams show no significant change in deformation rates or patterns that would indicate increased volcanic hazard at this time. So no change in the imminence of eruption there. They do note 134 small magnitude earthquakes, all below magnitude 2.5, below the summit and upper elevation flanks. Right, not just the rift zones, but upper elevation flanks as well. And mostly at depths less than 5 miles, 8 kilometers below ground level. Right, they do note here the GPS measurements. GPS measurements have recently shown a change to contraction at the summit, which is most likely due to a deflation of the shallow summit reservoir. So that is something to look at as well. Deflation of the shallow summit reservoir as a likely possibility for the signals, and they can see a lot more than we can see publicly. So probably all the GPS signals in the short term are pointing in a manner and a pattern that suggests it is that shallow reservoir source rather than the deeper dike source, which are the two elements in play for Mauna Loa here. Nothing with the gas, nothing in the webcams. That's it for the Mauna Loa there. So I wanted to show you guys superimposed here. I actually have plotted since November all of the earthquakes bigger than magnitude 1 on that InSAR image. So you can see this current flurry cluster that's been ongoing for over a week now. That's north. This is just off of the map here, just off the side. Right? That's where they fall. You can see that that's a deeper source, and that the broad inflation source is really focused more in a summit region right over here. Right? I've drawn on here the rift zones, so you can see a little bit of the shape of where the rift zones are, and you can kind of see that the summit here has earthquakes in that band where the summit and rift zone, it's really in that swath, more so when you get to that shallower region. So it does seem to be following that filling pattern, that longer pattern, right? It's really asymmetric. It's more long in that direction than it is wide in this direction. See, maybe the yellow is better. More long in that direction instead of wide in this direction. As far as that cluster of earthquakes, right? It's kind of aligns with the rift zone a little bit like that. And so that northern station is right over here. The southern station is right over here. That's a GPS distance measuring a distance from there to there. And so this is a zone. You can see that the summit inflation zone is broader than that over here. And so that means there can be filling happening in these outer margins over here that's on the outside of this station or on the outside of this station possibly as well. Although the signal we're seeing here, it's hard to tell whether this has been processed for any kind of asymmetry, different look directions, integrations for time, and all of that. But we do see what apparently is a bigger fringe here on this northwest side of the feature. And so maybe that's something to do with that, or maybe it's a result of the look direction, because we do see a similar pattern to this asymmetric with this little tail here that sometimes happens when the satellite's looking from over there. So unclear here exactly what how that relates. But I'll zoom it out one more time, and so you guys can see that fairly small extent of the InSAR image right in there, compared to those summit earthquake swath right through there, that northwest patch right in there. Pahala earthquakes are this big blob down here. This goes back through November, beginning of November, so this precedes the Kilauea ongoing eruption. It includes a buildup to it. So we can see Kilauea summit, caldera, and Upper East Rift Zone here as well outlined in this earthquake map over here on the right. Okay, it's also notable that there are earthquakes happening. These two yellow ones over here, those are that recent 4.3, 3.9 in this Kilauea area. Right, this is one of these areas of Mauna Loa's flanks that's important. That we'll bring up again when we talk about the research. The Kauiki we've talked about several times. That's over here. Kauiki area. Earthquakes still activating Kauiki quite a bit, probably more so than other areas so far. But there are some earthquakes here in this upper Kona patch as well. Right, so that would indicate some movement of that flank away that way, movement of that flank away that way, and movement of this flank away this way. So it's kind of filling and spreading and pushing out a little bit on all sides. And it's really a question of where is it going to pop and where is it going to give the most, as giving an indication to where an eruption might happen following some pattern, right? So all this is accessible on the USGS monitoring page. I cannot get that to work with this browser, so I'm not going to go there. But if you do click on these stations, the ones that do work and provide direct links, you can get data like this. And this is the MLSP, right? Mauna Loa South Pit. This is a southern station, now broken into components of east, north, and up. If I scroll it down here, you'll see that the length of time goes back to 2019. This is a 2-year plot. And so it's much more compressed here. We're going further back in time, so that previous plot was just the right half of it here. But we can see the signal broken into north, the up being a little bit less, but the north being the component, the north-south distance being what changes the most. Not a whole lot of change in the east-west up there, actually, right? So most of that change is happening in the north direction. You can see from that MLSP. So it's possible with this data to actually go through all the Mauna Loa stations. Here's a little sample of some of them here. So southeast flank and Ainapo Trail. That area is also moving back to the north slightly here, but not much change in the patterns otherwise up in the east. Maybe slight changes in direction, but on the east here a little bit. Right. On the west flank at Pohaku Hanalei, also above 12,000 feet, we do see a change where it is moving more to the east, so sagging more in the opposite direction than we have seen, and otherwise fairly steady in the north and the up. And so it seems to be still rising, broadly swelling from below, but that upper part of it's tilting back to the east at the same time. And that's an interesting thing to note, because that's where that broad inflation is coming from. With these other signals, there might be smaller variations on top of it there. West flank at Sleeping Cave, 10,000 feet. Really don't see much change there on the east or the north or the up. Right? We're not seeing that inflation reaching down to these lower levels. 10,000 feet is not really apparent there. We don't see it at 8,000 feet, 8,600 feet, Opakahuku. Right? We actually are going down very slightly. Same, not much change in the patterns north or east there. Going a little further, Ocean View, pretty flat, slight little variation, but the scale is so small here that this really could just be some interference. The trend's really not any drastically different there. And Pi'ikea, upper Pi'ikea, 75, 70 feet elevation, not a whole lot of change there as well. Looking on the northeast rift zone, you can see those signals are all flat. Not a whole lot of change there. Maybe some little variation on the northeast flank at 7,800 feet, but same thing where you really don't see a lot, and it's not very sharp or very quick. Right. Otherwise, there was a bigger adjustment you can see on the northeast flank, 6,600 feet, going back to the start of Kilauea's eruption, right? So this is actually feeling now Kilauea to its southeast when you get down over here. whereas some of the other stations are not going to see that signal there. So those are all different stations from Mauna Loa. I've not been able to plot the vectors for all of them very recently, but we can go back to the vector plots brought up by USGS before. So you can see north direction, east or west direction combined can give you an arrow like that, right? So that's what these arrows are actually showing you. The direction that each of these stations at the bottom of the arrow, where those stations are positioned, which direction they are moving. So this interval is July 2020 to January 2021. It's a six-month interval. You can see that over half of the year last year that this northern MOKP station is actually moving to the southeast towards the caldera, right? So you can see here that this ALEP station is moving much faster. The length of the arrows corresponds to the relative magnitude as well. So if it's bigger, it's moving faster, right? So this one is moving faster in the opposite direction. So that indicates that somewhere in the middle of here is where you have the source that's pushing things in both directions away, right? You maybe don't only have one spot because you can see that some of these are pointing more that direction. So it's actually believed that you have your shallow, your magma chamber somewhere in the area of that southeast part of the caldera up here in Mauna Loa. So you might have some more localized something going on in here, but also you have something going on out here, which is interesting. You have a combination of both those things, kind of two superimposed signals. So I'm going to leave it at this kind of weird scale so I can advance it and not change the view for you guys. And MOKP in the period between October and January, this is wrong, October and January doesn't show much movement at all at MOKP. Whereas you do see overall all the other stations still showing that broader movement away, right? So that broader movement away might be that deeper structure, that deeper filling dike that's a longer feature, something like that. And you also have some other stuff happening with the shallow magma chamber, magma reservoir. It's hard to call it a chamber because it might just be a network of lots of different parts of magma, bodies of magma. So a reservoir may be better. And then also that deeper source that's somewhere over here. So deeper source, and maybe that has affecting some of the signals in this area as well. Okay, then if we advance, this was all from the USGS Volcano Awareness Month, when Mauna Loa Erupt Next presentation by Frank Truesdell. And a period that goes just from December to January 2021, MOKP was actually moving in a western direction a little bit, away from the caldera. So what you can see essentially is that there can be some small scale variations within that broader scale pattern of summit inflation and filling, maybe maybe not quite in a round fashion, but maybe more of an oval or asymmetrical fashion there. So that may be part of what we're seeing here. The shallow earthquakes are somewhere in this region closer to this shallow magma chamber, right, which is not very well known or quantified. The ranges range from being about the size of Kilauea's South Caldera chamber to being a little bit bigger than that, to being a little bit smaller than that. So it kind of depends on who's modeling it and what assumptions they're making and what numbers they come up with. And we're still waiting for better information due to ground movement on that. So we'll look for the next iteration to see what shows up here. Whether we have some shallow, deflating, smaller source within a broader pattern of inflation, we'll have to wait and see. Yeah, but certainly we know that what's happening is this contraction, whether it's deflation happening or combined with something happening over here in the northwest. We'll have to wait and see when the next satellite pass comes back around. We do have InSAR from other points in time. So going back in time, this is the previous InSAR that USGS shared. Was from between March 2019 and December 2020. And so you can kind of see this double wing pattern, kind of butterfly pattern that's typical of these tabular dike-like features as they fill up that deep part of the mountain, right? The Mauna Loa southwest rift goes off this way, and its northeast rift goes off that way. So you can see why a dike, that deep dike system, lines up, and it's easy to fill, and essentially is interconnected with that shallow chamber a lot of the time, depending on the dynamics in there. It can be apparently fairly free flowing between them. Right? So unlike other rift zones that have a bend, right? Past this northeast rift zone bend, or past the southeast rift zone bend on Kilauea's east rift zone. So this was the previous one. You see butterfly pattern. You can see, up here with a broader signal as well. Right. One before that was from January 2019 and January 2020, and similar butterfly pattern with that broader pattern as well. So this has been going on for a while, is my point. You can see that this is, as long as we've been getting these, this is January to June 2019. We've seen similar butterfly patterns with that broader inflation. So that's all the same as we've seen going on there. And going back to the point in time where 2002 to 2007 is a special case. And so here's the InSAR averaged and broken into its components InSAR from a paper we'll talk about here next, as we switch gears here and go into our deep dive on Mauna Loa. So we'll take Mauna Loa questions at the end here so that we can cover a lot of this why and maybe lump it all together here at the end. But so start off with this view here of the 2002-2007 InSAR showing that butterfly pattern at the summit of Mauna Loa and that overall broader zone of swelling. And to put this in context, here is a GPS and EDM combination plot. This is distance change in centimeters here on the left, and this is across Mauna Loa summit as well. So the red part of it over here, that's the GPS we're looking at. So down here at the bottom, 2002 to 2007 is right in here. I'm going to zoom in so you guys can see it better. You can see that the distance across Mauna Loa was actually contracting for a while, and right in here is what we're talking about, 2002 to 2007, before it seems to stabilize again. So this period of change right in here is the one we're going to examine, right? So you can see that there was quite a bit of spreading across Mauna Loa, and then it stabilized and flattened after actually being fairly steep at a couple of points right there, right? To show that the volcano can fill without erupting, as was the case here during this epoch. All right, so you can see there was actually we'll come back around to this, but 2015, and another little post comes in that corresponds to some earthquakes as well. But we'll get to that here towards the end as well. But first, we'll focus on that InSAR image was brought from this paper, which is Science Magazine 2007, Stress Control of Deep Rift Intrusion at Mauna Loa Volcano, Hawaii, by researchers both at University of Miami and at Stanford University. And so I won't read it for you guys here, but I can show you guys that they integrated between 2002 and 2005 the InSAR for that entire 3-year period, right? I'm talking about all the way to 2007. They went to 2005 here. At the time that they published this, it was still ongoing. And they see a similar kind of butterfly pattern here and here as well on the summit. And it's a little bit, to show you guys some of the complexity of InSAR, this one actually is showing us the look direction, right? So we're looking from this angle over here. So the scale is line of sight velocity, with reds being positive, right? So we're looking from this direction, so we can see that this is actually moving towards us, or negative on the side. This blue one is moving away from us over there. So that's the difference there. Let's see if I can. So they've actually broken it down into components here, which is something you can do. You can extract it, and we're not really clear what that previous image was there, but you can see the vertical here, vertical coming up. You see both sides, that butterfly pattern there on both sides, and they have actually put on here for what they use in their model, the length of their dike and the plot of their summit magma chamber right in there. Summit magma chamber right in there. And east-west components, you get that similar different colors because one's coming towards and one's away, but that's a similar symmetry right there as well. All right, so that's just showing, the InSAR. The InSAR is a basis for a model that they made. And our model essentially goes through and using that dike as a big sheet, which is kind of the grid here, and these little squares are blocks of the grid, and a magma chamber that's it's right there at that upper part of it, at similar depths. As magma can fill both of those areas, what signals would it induce on the surface? And they're trying to match those surface signals to the ones you see on the InSAR. And so they've done that pretty well. And their model, which is not necessarily unique, there may be other ways to do this, but this is one solution that does work, is that you actually had, in this period, 2002 to 2005, magma was filling down from close to 15 kilometers deep, right, all the way up to the depths of that magma reservoir. And so quite a lot of it, in fact, they say 80% of it comes into this deep part, what you might even call a deep rift, perhaps, right, deep under the sides of Mauna Loa, right, the southwest, a little bit more in the southwest, with not as much above it, and a little bit more even on the northeast over here, and focused more so in the shallower areas, but not exclusively by the magma chamber, magma reservoir right in there. You can see it certainly focused close to there, but quite a lot of it in areas that are outside of that as well. So there is a big component of this that actually is this big tabular body, and a smaller component of it that's this magma chamber superimposed on top of it, right? And so that's what they've modeled here over 3 years, opening of centimeters per year, right? Close to an area is close to a meter of opening, right, underground at these depths, to allow all this magma to fill to the area. So quite a lot of magma coming in there. A big supply that's actually larger than previous eruptions of Mauna Loa, but did not cause an eruption this time because the volcano was able to deform and swell and shift to accommodate it without having it reach the surface. And that's something volcanoes do as well. That's why magma movement in volcanoes is so interesting, but it's not always something that is going to lead to an eruption, right? And it seems like Mauna Loa is just a matter of time. And in 2002 to 2005, we're wondering, what's going on? Is this going to lead to an eruption? In that case, it didn't, just to show that it doesn't have to go all the way necessarily. All right, but also in hindsight, this is going to give us the residual of what we're working with here, with what the magma system looks like recently, and where magma might be filling in soon, or has been recently, because this paper does go back 14 years now. So up here is the actual data measured by the InSAR, and you can kind of see the different look directions plotted above for each column. And their model predicts very similar patterns there, right? And so you can see that the look direction is more from the northeast, we'll call it, over here. You see a larger asymmetry. I'll zoom in on that. Your look is more from the northeast here. You have larger asymmetry towards the southeast. And if your look is more from the northwest, you have more of an asymmetry towards the northwest, right? And sometimes you do have these little tails that can flare out here as well, right? You see more of a tail on the south side than on the north side over here. So it's interesting to see that, and to think about whether that's something we're seeing in that most recent InSAR image. Don't really know. I'm just showing you guys why you might be suspicious of that. And then you can see here at the bottom, modeling the data to the actual line of sight change. All right, so that's how they fit their model, and they're just showing the results here. And then they show us a series of cross sections. So most of these are going to be moving from the northeast A prime to the southwest at A, right? Looking along this dike feature, along this rift zones, not all the way to the ocean, right? Just this upper rift zone area, really, there to there. And then we'll look at one last figure that cuts across of it, B to B prime over here. So starting off with over here, looking incrementally, they start back in 1983 earthquake. That was the Kauiki earthquake. And that earthquake was a 6.6. It was in November, right? It preceded the 1984 eruption. It was the harbinger of that eruption, the earthquake that's associated with that eruption as being the one that essentially unlocks the volcano's pressure to allow that to happen. So here's what they're showing. Because they can calculate where the magma is filling underground, they can then predict what the changes of the pressure, which is in 3 dimensions, we call it stress, how that actually propagates, right? So you can see that earthquake happens more close to the northeast rift zone. Clamping essentially means tightening of that area, right? So less conducive to filling, and unclamping, less pressure, where it's more conducive to filling. So you can you can really see that the area to the northeast is closing, and the area underneath the summit is opening prior to 1984. You advance it 1 frame, and you look at the 1984 dike. Right? So that magma did come up into that area. This blue area is where it actually emplaced. And where it in place, it actually tightens things up because it's filling that zone and pushing on the sides. But the areas below it that mobilized, perhaps, or are adjusting differently, are now more conducive to follow up filling of magma from below. And so that's 1984. And so you add both of those together, the 84 dike and a 83 earthquake together, you have a situation where you close off this area over here to the northeast, you close off a little bit more of the summit, but you do have inclination for more opening in this deeper part of the rift zone right in there. Right? And you can see that perhaps a little bit more to the southwest. It doesn't really go all the way to the edge of the graph here, right? So it's really more in a summit region. There's a summit caldera. The northeast rift zone being a little bit more complicated over there. Right? So that they're saying that when it comes time for the magma to fill 2002 to 2007, it's going to go right in there, and that's where they see that zone of filling. So they've superimposed on here their little blue dots, and you can see that it matches pretty well to this zone of unclamping that they put on here, although you can see that they actually left off the dike in this particular image there. But that's essentially the state that resulted after 2005. So altogether, they put it like this: cumulative change of 2005, and this went on a couple more years, but they're suggesting that what's left over are zones in the upper southwest rift at shallower regions, or under the northeast rift at both deep and shallow regions. Both of those can occur. So you can imagine if magma is coming to the volcano, as we believe it has a few times since then, and appears to have been the case recently with the GPS trends as well, that magma continues coming to the volcano, it may well have filled these areas. And so these are the areas that maybe are the ones that have been filling and pushing on the volcano and showing the movement of the faults. And so now we're going to move to that cross section that goes from B to B prime, going from the west to the east over here. And the dike is shown as this black line, and we're looking at it on end. And the magma reservoir is superimposed right there. You can see it there. And you see a similar kind of view of unclamping and clamping, with more clamping in this zone around and above, with a little exception at the near surface right up there. But much more unclamping on the Kona side, along the base of this Kona de Colmont fault, and on the east side towards Kilauea on a Kauiki and Hilea de Colmont fault. Right, you actually induce earthquakes. Right, this is sea level right over here, 0. So you can kind of see that above sea level, not so much. Right, that's the above sea level ones. That's due to magma filling this upper chamber area. The below sea level ones, those are the ones moving the faults. And that 4.3 earthquake we just had was on this Hilea right there. We talked about the Kauiki ones as well. I've mentioned that we did see a few earthquakes. They're all on, the largest ones in the range of magnitude 3s on the upper part of this Kona fault as well. So we are seeing these things move. Right? So that seems like it could be more of that same happening in a grand scheme where magma is filling this dike and it's leading to this broader pattern. And then something funny might be happening with magma moving between that shallow chamber and the dike. Maybe you could have some localized deflation above this source, which you're only looking at as a dike on end. If you looked at it the other way, right, like we just have over here, then obviously the dike's much bigger than a magma chamber in that direction. So interesting there. So that's how it primes and how we could shift from having patterns of earthquakes at the summit to earthquakes on these fault zones down here. Right? So we can keep moving on. There's another earthquake by one of the same authors from the University of Miami here, but also by Thomas Walter, and volcano earthquake interaction at Mauna Loa. This one goes back to 2006. So in that similar kind of modeling paper, you see another iteration of what that looks like in a map scale here. Now I'll zoom in. But what essentially they say with that similar kind of model of magma chamber and dike is that if you have a dike in a shallow northeast rift zone, which we've said is one of the places it might want to go, you might have more earthquakes encouraged in this lower Kauiki area towards Kilauea. Right? So possible we've had some earthquakes in that lower Kauiki area. If you were to have a deep northeast rift zone dike, then you can have earthquakes that go much further into this Kauiki area. And we have seen that as well. We actually do see earthquakes popping all across here. So maybe that's some evidence for there being some deep northeast rift zone dike component in there as well, possibly, because some of these do have overlapping and non-unique solutions. Right? So you could have earthquakes here on this northwest side as well, you can see, that are induced by that, right? More so with a deep dike than a shallow dike. If we go to the southwest rift, shallow, you see earthquakes are encouraged, more so in the Kilauea area over here, a little bit in the Kauiki area, and in the south flank of Kilauea, the southwest flank of Kilauea, which is getting to be gray zone of whether it's southwest flank of Kilauea or the southeast flank of Mauna Loa. There's some overlap there. There are ones riding on the other. And you see that you would expect there to be less earthquakes in this Kona area, less earthquakes over here as well. So that would be for shallow southwest rift, less earthquakes to the northwest as well for shallow southwest rift. For deep southwest rift, you would see earthquakes across Kauiki and all of Kilauea and a good part of this Kona as well, especially this upper region up in here. Right, and this northwest part. So perhaps we have some deep southwest rift zone dike filling going on as well, just based on that, right? Based on where the earthquakes have been popping off. And just for comparison here, they do show inflation at 5 kilometers depth, where the magma chamber centered right in here would encourage earthquakes in that kind of zone. And so it does include a little bit to that northwest as well, and more so at the summit, and less so towards the coast there. So interesting to see what those predictions, right, are based on the models, the stress models there, and that leads to this whole cycle of what's happening on volcano like Mauna Loa. And you have some earthquake that happens, some movement of that flank that occurs, right, as labeled as part A right here. Here's our magma chamber and our dike drawn on this cross section. So you have some movement, whether it's an earthquake, a big one or a small one, whatever else. That leads to a stress change with the magma system. So that essentially makes some space for magma to come up and decompresses the chamber, unclamps the rift zone, and compresses the area below it, which is going to trigger and encourage magma to go and fill that space from below. And it can fill that space without erupting, as it is in the case here. Right, so coming injection into this area. That can go to dike intrusion and eruption. Right? So if it's actually putting out a new feature that might intersect the surface, that's something that can happen. It doesn't have to happen. You can skip this stage sometimes, where you can just go from it filling underground. You might have a dike that's underground just this size and doesn't get to the surface, perhaps, right? Or one over here as well, where something like that. So that can be but that's an important feature as well, because once that happens, that puts more pressure on a fault to the side once again, here and here, and that's going to lead to earthquakes as you see that fault movement. So here we have the cycle, right? So we have seen earthquakes on the flanks, right? Several times we've saw them in Kauiki in October when Kilauea was inflating and adjusting with Mauna Loa. We've seen them more recently than that a couple of times. Stretching into the magma system with unclamping and filling of magma, we've seen a long-term pattern of inflation at the volcano. That's there, right? We may see drops from movement of magma to some other areas. It may not be as simple as a sphere and exactly this shaped blade, right? Maybe if you have magma moving around, you can then change and have more localized signals, and that can lead to moving the earthquakes from being around a summit region back to the flanks one more time. So that's how you can go from flank earthquakes to summit earthquakes to flank earthquakes, and that pattern going on there. Right? So it does suggest that there is some movement happening in the volcano, and it could be because the flank moved there. And so similar to the Kilauea south flank moving, which one is the one driving the volcanism there? Is it the space being pushed? It's a little bit of both, right? The magma pushing, or is it, you can see that this, because Mauna Loa actually weighs down the crust, it bows down, and this is an uphill push for the volcano to get up over that slump, right? For the magma to push this material out of the way, it's going to push it uphill. So there's a natural resistance there that it wants to kind of keep itself clamped closed just by gravity pulling back on itself there. So you got to overcome that. All right, so one last thing, and one thing that we've been mentioning before is that there are patterns of eruptions and earthquakes being associated together. So we have here eruptions in triangles and earthquakes in X's. And if they're Kauiki and Northeast Rift Zone, they're black. If they're Hilea or Kona and Southwest Rift Zone, they're in gray. And we have magnitude on the right and eruption volume over here on the left. So you basically can see each of these bands up and down is where we had an earthquake precedes an eruption. This was magnitude 6 preceded eruption on Northeast Rift. Magnitude 6 again. Magnitude 6 again. Northeast Rift Zone eruptions. Magnitude 6 again.
Yeah, it's all too common right in there, those
Actually, no, that's 1868 one. That's a magnitude 8 right there, 7.9. And Southwest Rift Zone eruption there. There's Kauiki, Northeast Rift Zone eruption. That was a magnitude 6.5. 6.5 Kilauea Kona. Right, we're not even in 1900 yet, right? Not all the time. There are times occasionally, right? There's an earthquake, didn't quite have an eruption. There's an eruption over here that follows a little while later, not quite so as close in time, so they're not always that close. But maybe you could be a little more generous there. Maybe you have an eruption that doesn't have one earthquake. One earthquake preceded 2 eruptions in that case, right over here in the Southwest Rift Zone. And so maybe you can have something funny happen. Not exactly all the time, not guaranteed. Right? Here's some earthquakes with no eruption that followed. Earthquake, then earthquake, eruption pattern, right? But we haven't had anything of this size, magnitude 6 or bigger, in any of these zones, Kona, Hilea, or Kauiki. Right? So that's something we're still waiting as a sign of, well, where might it go, northeast or southwest, based on that triggering. Right? So just wanted to show this. That's also matched by this model here. Why you
Makes
have
for a good oracle.
Yeah.
Makes for a good oracle about, just getting a little bit of insight on what to expect. And that's why when, like last times, the 4s and 3s we'll see on the Kauiki and the other way around the summit, it's just not the big ones that we're looking for. And
right.
As we said before, Mauna Loa is the queen of pump faking. For those that don't know what that term means, it means just to fake something to draw the opponent that's watching you off sides. It's a football term, but it really fits Mauna Loa sometimes.
Yeah, there's one last caveat I got to add on here at the end. When this is a map that comes from the fact sheet of Mauna Loa here. And this is a map of all the radial vents on Mauna Loa. So it's not not a whole lot of eruptions come out of the radial vents. Something less than 10% over the history of the map flows here. But you can See, all these red zones are areas where the magma is not behaving in this perfect dike and magma chamber situation there, right? There's got to be some blade, whether it's a flat blade like a sill or a dike that's more vertical, or there's some pathway of magma that clearly exists here, especially to the north and to the west. Right? This is the zone of radial vents. And from 9 o'clock, 12 o'clock, that's the sector of Mauna Loa that has them right there. There's there's similar complexity that, that when we look at that pattern of 2002 to 2005 to 2007, that's fantastic to see how that manifested during those years, but that's not the only way that it can happen. Right? We have other structures, like as you can see here, that can get activated sometime, including this big gray one is a 1859 lava flow that went all the way to Halemaʻumaʻu Bay, right over here, right? So these can be pretty big eruptions as well, tapping, part of the sequence in the magma body too. So it's clearly not as simple as just the sphere and the blade. But that's a good place to start, right? And then we put on a wrinkle and throw on a wrinkle and throw on a wrinkle, and the trick is to keep track of all the wrinkles that exist there. So yeah, that's the first part. That's the first part of it here, and we can take a little break if you got something you want to add, Dane.
Yeah, is each one of those little markings the radial vents?
Each one of those little markings is a radial vent.
So there's 33 on there.
Well, so there were 33 radial vent eruptions, I want to say, right? But as you can see here, if I zoom into this 1859 one, they're actually marking individual vents for the same eruption. 1, 2, 3, 4 upper vents. There's these other side vents over here, right? Okay. So that 59 eruption probably has 7 red marks on here, as an example, right? So these could be related. But just to show you, those are all pathways of magma to the surface. That is my point here.
Right. We do have a question about the radial vents here. So we'll start with that one since it's right in the line. Why are there no radial vents on the east side? Is the first question about them. And it also, they say, just to continue with it, that was from Jari, and Matthew asks about why does Mauna Loa specifically have radial vents, and how do they form? What's the reasoning behind it? Yeah,
that'll be a different in-depth dive some other time to go into all of that and go into all the research of that, right? It's thought to do with the fact that this west side, so of all Mauna Loa's flanks, they're not all exactly the same. The southeast flank especially has got Kilauea on it, and all the interaction that happens there. And this southwest part of it is actually the most free part of it that can move more freely. Right. So you have other areas over here that maybe can't move quite as much because you have Hualai and you have Mauna Kea, and it might have something to do with the nature of the flank, right? And I'll kind of leave it as a teaser at that before doing a deep dive into that. But it's something to do, it's thought to have something to do with that.
Right. I do have a quote, but it basically sums up what you were just saying there from USGS about the free-moving flanks and the radial vents and how they relate, from an old volcano watch from 1997. Says, in addition to the rift zone, Mauna Loa has radial vents. Radial vents are eruptive fissures on the southwest, west, and northwest flanks of the that are oriented radially to Mauna Loa's summit and are located outside of the defined rift zone and summit regions. Because Mauna Loa is such a large volcano, pressures exerted by the adjacent volcanoes do not affect the free-moving flank, the South Kona flank, nor do they affect the flanks north and west at higher elevations. Thus, radial vents can form in geographic regions away from the rift zones. It's kind of just a teaser from USGS, a couple decades ago. But
yeah. So we'll look at that more detail a little bit later. Yeah, I do have a little more. If you have more questions on Mauna Loa, a little bit what we've done, that's cool. But as far as connection to Kilauea, that's what we're gonna do next.
Okay. All right. Let's talk not about connection to there, but Marin Purvis asks, our moderator asks, are the Pahala earthquakes much deeper than the Mauna Loa Kīlauea fault earthquakes? What's the depths that we're talking about when we're talking deep earthquakes on the Pahala region versus
Right.
the shallow earthquakes at the summit. We talked a little
Right.
bit at the sea level and above sea level, but
It's similar to the South Flank Kilauea earthquakes, right? So you see those depths that might be in a 5 to 10 kilometer range, something like that, right? You might be 3 miles, 3 miles down, or more. Whereas those deep Pahala earthquakes usually start around 18 miles down to 20 miles down, 25, 26 miles down for some of them. Or in a range of 30 to 40 kilometers, right? So there's a gap in between there, and usually if it's 10 kilometers or down, that's that flank area, that's moving. So yeah, shallower depths than the Pahala earthquakes, which are more the feeder source. So Mahalo Marin.
Yeah, this is an interesting question here. Ms. Stitcher asks. Says that understands that Mauna Loa is untouched mostly by human development, with it slowly, waking up as we've heard before. Could there be more roads and possibly a viewing area established now, before it happens? Is the question. Now, the thing for context about that, for people that don't know, 2018. It was a constant battle about lava viewing. You had people that were living, having their homes taken by the lava flow that weren't allowed to even go and see the lava. People getting cited for taking pictures, getting removed from areas that they had access to do evacuations because they had taken a picture, just absurd stuff like that. And promises the whole time along of, oh, we're going to get a viewing area. It'll be a nice viewing area. We still don't have that viewing area, right? There's still no official viewing area for that eruption. So that's kind of like where I think this question's coming from.
Yeah,
take it from there.
I mean, Mauna Loa summit's so remote. It's anything that's gonna happen at the summit is it's gonna be for the adventurous only to hike at high elevation, and even then there might be closures for safety reasons, right? It really depends.
Yeah.
The caldera is big, the crater walls are deep. So maybe there's a way that if there was some eruption, you could hike up there, and whoever could make it. Right?
Yeah, it's going to be hikers, though. It's not going to be like we're going to build a road to the summit and people are going to drive up there and view it. And the thing about Mauna Loa is it's so big that good luck predicting where the next rift zone eruption happens. Like, I wish you luck with that to guess correctly.
Part 2 is the prediction. The prediction part being impossible, right? But part 3 maybe being a more important part is. When Mauna Loa erupts, its volumes are much larger than Kilauea's, by and large. And so the first thing you want to do is run for it. And much later, do you want to worry about, can I get a safe viewing area put up? Right? It's
right.
Kilauea is usually I've called it the Goldilocks volcano in the past, where it's erupting just enough to be interesting, but not too much to be super dangerous for the most part. That was until 2018.
Yep. All right. So we have a question here about. We'll use this as a phase into because you're going to talk about Kilauea and Mauna Loa influencing each other in the next segment. But this question asks about if Mauna Loa were to have a big earthquake, could it influence Mauna Kea into doing something unusual in terms of activity, turning on, increasing volume, in those types of ways?
Right. For Mauna Loa to do something interesting, funny, volcanically, there has to be some other independent magma movement. Right. So the magma movement would have to be from something from deep down. So if there was, let's say, some earthquake swarm that gets detected that corresponds to magma movement under Mauna Kea, and the volcano gets primed to some situation, and then at that point an earthquake could maybe set it off, but you'd have to prime it with the magma moving itself first. The most recent signals from Mauna Kea have been periodic earthquakes that seem to correspond to, from the most recent research published, maybe correspond to actual cooling of the magma chamber, and not fresh magma coming into it at all. So there's no sign of that happening in any way whatsoever. You'd have to have starting from scratch magma coming in from deeper down, which is possible from that whole hotspot track and all of that. It would have to come from deep down, and you'd see the signs of it coming before you had the one that set it off to actually cause it to pop off. And the pressures from coming from deep that far down may be so much greater than the surface earthquake that it's really, you know, like the straw that comes back if it doesn't come up on its own already anyways.
We have a $500 super chat from Arlie Jefferson. Says, thanks for dropping all the knowledge on us. I feel like viewers should get college credit. Wow, like, that's insane.
Arlie, I really appreciate that.
Yeah, that's great. Amazing. I think a lot of these questions.
Yeah,
okay, this is one that's good. This is one good one that you were talking about before. Does deformation data indicate the caldera clamped instead of unclamped rapidly lately, since it says that the distance of the caldera walls is contracting? When we've been talking about that in the last couple of weeks. That's a question from Joey.
Yeah, it's hard to say it exactly like that. I mean, that clamping in and clamping is a measure of the pressure changes, you know, within those areas, right? So you may not actually have the rocks moving per se, right? As might be related, because if I'm pushing my hands much closer together, it's much harder to wedge something in between there. And if I'm not pushing as hard, then I can wedge something in there a lot easier. And that's essentially what that pressure is, right? In that dike, pushing on that magma. So if it's a little bit less and you have pressure from below, then it can fill it in, is the idea. So if you have it unclamping, it then leads to magma coming in, which then leads to the caldera spreading, usually apart, right there, yeah. But for that cross caldera, you know, that measures anything coming in directly between in those stations, right, from north to south, from north Mokuaveoveo station to Mauna Loa South Pit station. So that's the difference. That's the difference there. So as we saw, the inflation area is broader. So if you had some injection that was outside of that, you know, north of one of those stations or south of the other one, then that line might show a different movement. It might show what I would call in that case a localized contraction. It might be because of localized deflation, right? But the broad pattern overall across the whole volcano as a whole, I think, is, in the long term especially, is still is that of a broad slow inflation. And going through that cycle that I just showed you guys, the cycle of you see the earthquakes in the flanks, and people say, oh, there's earthquakes in the flanks, it's going to erupt. Like, no, that's just the flanks, it's just a fault, it's moving, it's okay. And we see earthquakes at the summit, oh, it's going to erupt, it's earthquakes at the summit. It's like, well, that's just the summit adjusting to magma coming into it, and then it's going to do that again, the flanks, and then the summit, and then the flanks. And it's more about when you have the background rate going up, right, and then you have more drastic GPS signals, then you might say, okay, now it might actually lead to an eruption, besides this filling with magma that it's doing all the time, right, episodically.
Yeah. Hearing about Mauna Loa filling with magma is about me every year I've been on this island for the past 15 years hearing about it, you know. So it's always about that next thing, right? You tell me Mauna Loa is filling with magma, I'm like, okay. But that does it for this round of questions. We will be doing one more round when Phil goes into this deep dive on the connections of Mauna Loa and Kilauea. Back to you.
All right. So we talked about, I brought this graph up last week, and this is just showing Mauna Loa eruptions on the top and Kilauea filling rate at the bottom here. So the idea being when the filling rate is steep, like down here, there's a lot of magma coming into Kilauea. And when the filling rate is flatter, there's not as much magma coming to Kilauea. And during that same time of less magma to Kilauea, you have a lot of activity in Mauna Loa. And when it gets steep on Kilauea again, you have less activity in Mauna Loa. So this was this is one way to look at that correlation between eruptions, right? So we will look at a little feature here that dates back to 2002. And this was an unexpected interaction between Kilauea and Mauna Loa, as shown on a GPS here. And so this was a nature brief communication here in January 2003. And I'll show you guys the key figure here. All right, we're looking at similar stations here. This north station, MOKP, MLSP, and then we're also using this station as another measurement there. So you can see, for example, The light blue arrow is January 2001 to May 2002, and the dark blue arrow from 12th May 2002 to August 2002. So you see similar, that flipping of the arrow at this north MOKP station, right? Times where it goes towards and times where it goes away. That same kind of variability we're seeing now is an interesting part of this too. Right, okay, so that's where we are. And the interesting thing here is that you see, well, let me go here to the left and show you guys, this is distance change, centimeters. The red station's Kilauea, and the blue and green stations are Mauna Loa. One is to the South Pit Station, one is to that East Station. Right. So Kilauea's at the top. You can see that in late 2001, early 2002, Kilauea starts spreading apart. That's magma coming in Kilauea summit right here. And it turns out that about 6 months later, you see magma coming into Mauna Loa system. At the same time as that beginning is marked, there's an eruption on Kilauea. So Kilauea's slope changes here because it actually enters eruption. And eruption changes right over here. And that's why it leads to that change. And so they're saying it's really interesting that for volcanoes that aren't connected, that you would see what appears to be a surge appearing on Mauna Loa at the same time as a surge comes into Kilauea to the point where it bursts to erupt in a different way than it was before. Right, so that was kind of the basis of it. And from that, after some years of research here, famous paper from October 2012 by Gonnerman et al., Michael Poland from USGS, a lot of UH Manoa authors here as well. But coupling Mauna Loa and Kilauea by stress transfer in the asthenosphenic melt layer. And that's probably a lot of jargon for a lot of people. So we'll break it down here. Right, so they're showing models of Kilauea summit, or I'm sorry, Mauna Loa summit and Kilauea summit over here. And similar, there's those two summit stations, and they're modeling their summit reservoir a little bit bigger, but there's our reservoir and there's our dike. And Kilauea has a smaller reservoir and a bigger, deeper reservoir. And there is this East Rift Zone pathway. And at the time, 2012, this is prior to any of the 2018 activity that ends all this, right? So magma is flowing out only through the East Rift Zone in this case, out of Kilauea, and that's why they link in the East Rift Zone here. So what they're describing, in fact, is that there's something akin to like a foam layer, something like a foam layer that exists at the top of this asthenosphere. So we've talked about how through the crust, the magma coming through the crust comes in two separate pipeways, and that's indicated here by these two red arrows. Right, there's an influx that goes into Mauna Loa and some influx that goes into Kilauea that can both feed summit eruption, summit and East Rift Zone eruption, and also feed deep rift zone storage. Right, so they actually calculated filling of the deep rift zone by movement on the south flank, how much would fill as well to include that in their model. Right, so they're also saying that there's a big zone where magma is coming up equally through the hotspot coming through there, and it appears that there are through this zone of foam, which is somewhere in a range of 45 kilometers down. Right, so this is down below where we're seeing those earthquakes. Those earthquakes are happening above this area. Right, those deep Pahala earthquakes are above this, so this is under that. Right, there's a boundary between that denser rock of the mantle and the more fluid mantle and some kind of foam layer that they're hypothesizing exists in there. And it's through that when the hotspot magma's coming up, it then flows laterally through that layer and then comes up to these vertical pathways. And so that's what these little red arrows down here are showing, right? That there's a different pathway for magma that goes Kilauea that is independent and might have a different chemistry entirely than the magma that goes to Mauna Loa that goes this way and then comes up. But there might be some that's a little bit more mixed, depending which batch of magma it is that's coming up and where exactly. And so they've calculated all this out and matched it similarly to that period that begins first in what I just showed you guys in 2002, but also to that surge that followed later from 2005 to 2007. So I'm going to take this here, maybe one little plot at a time. And so this upper one here is showing, on the left, is showing magma flow rate, so how much magma is coming into the volcano. Or I'm sorry, flowing out of the volcano. In this case, only through the East Rift Zone is the only place it was flowing at that time. So that's this bottom red line right in here. And so you see it was flowing out of the Rift Zone a little bit more, and then the Rift Zone got blocked, and it goes down a little bit. And then it got unclogged and came up a little bit, and then it was steady, and then it started closing off a little bit. You can see then it really spiked right in there. Right? And then it came back down again, and it was pretty steady, and then it dipped and then spiked. Right, that's the output of lava from Kilauea. Right, that's measured by proxy by SO2 emissions from the East Rift Zone. Right, interesting how that ends up being, once again, the proxy for flow rate is the SO2, and that's why we come back to that here in 2021 as well. Right, so that's the East Rift Zone, and they've modeled here. So these little dark gray circles are summit SO2 emissions, which are related more to the degassing of magma coming straight up into the system before it flows into the rift zone. Right, so that's a better approximation of the input from the hotspot directly, we think, partly because a lot more of the CO2 comes out of Kilauea than Mauna Loa as well. So that seems to be some integrated version of both of the volcanoes there. And their model has the surge of magma coming in here right around 2004, where it comes in most quickly, and then tailing off through about 2007 before we're back to background levels or so, 2008 or 9. Right, that's the hotspot track, right? The hotspot input right in there. Okay? And the scale of CO2 is over here on the right. That's how they've superimposed it here. Okay, so that's our pulse of magma that came in, and they're saying it didn't come in just to Mauna Loa during that time. It came into Mauna Loa and Kilauea both, right? And so that's 2002 to 2007, this whole period in here. And that first thing we're looking at was 2002 earlier, that first article we just saw. So if I scroll down here, now we have in blue dots or red dots either the Mauna Loa GPS distance at the summit. That's this blue line that goes like this, right through there. That. Maybe I should make it in blue. Blue line and goes right there like that. That's that blue line Mauna Loa, actual Mauna Loa data, right? Showing. I don't know if I can zoom in anymore, but we actually show here Kilauea in the red, rising up, then flattening out, and rising up as well. There, that's the Kilauea line. Turn it back to red here now, I guess. Kilauea line. It's like that. And you also see this other red line and other blue line, that's the model bit to the data. So not quite exact. You see there's a little bit of variation, some imperfections in the model there. But they're approximating the pattern that was seen here. Right? Both on Kilauea and Mauna Loa. And so one thing that's interesting to point out here, let me skip the bottom one for now. They point out that during this period of time in 2001, 2002, when the East Rift Zone got blocked and the Kilauea's East Rift Zone rate goes down, that you actually see a rise in the Mauna Loa rate at that point in time, down in here. And that's at a time before you have the surge, you do see them kind of anti-correlated there. And then during the surge, they see magma coming in to the East Rift Zone, coming out of the Rift Zone, so Kilauea is flowing quite a bit there. And Mauna Loa, which had been on a steep upward track here on a blue line, back to blue, because the East Rift Zone really kicked in, Mauna Loa's line flattens out. They've drawn on here this dashed blue line. If the East Rift Zone had stayed down, what would Mauna Loa line look like? It would look like that, but because the East Rift Zone kicked back in, Mauna Loa line flattened and actually slow down because of East Rift Zone, because Kilauea was flowing. Mauna Loa's rate slowed down. That's what they're showing here. And so here they actually have the change in the stored volume of magma, cubic kilometers. And the red line is Kilauea. Kilauea had more magma come in here from 2005, 2009 as well, right? That kind of led to that whole 2008 opening of the lava lake. And we'll look at what happens after this period of time coming up, because there was more clearly that led to 2018. But this is a point where the average volume of Mauna Loa eruptions in the past century, volume of the 84 eruption, and here is just since 2002 how much volume we've gained inside Mauna Loa. So far, we've gained more than the average. We've gained almost as much as came out in 1984 eruption already up here. So the magma is coming in, it's just not erupting, right? And because we have a long interval and the flanks are moving, and maybe it doesn't, it has to erupt at some point, but it can come in at times more passively. And the question came in earlier this week: why has Mauna Loa's activity possibly been lower in the last 40 years? And one of the things happening in the last 40 years is Kilauea's East Rift being a pretty constant source of output of lava. And so it's interesting to see that there in these models here. So I think that's there. That's just to show that modeling changes in pore pressure actually can translate to changes that essentially work their way down Kilauea's Kilauea's input column, like slight little changes in the flow path, very, very small ones that add up, and at some deeper point actually can affect the pressure in Mauna Loa, and the balance between the two actually goes back and forth. They mentioned that it's actually about a 6-month delay, from something changing on Kilauea's output to a manifestation on Mauna Loa, and that's based on that 2002 data here. If I can get it any closer here. The blue line is Mauna Loa. Mauna Loa starts coming up right around there. Right, the Kilauea inflation is right over here. There's a little delay right there. Mauna Loa came 6 months later. And that's based on their diffusion rate, the pore pressure, to go down that conduit, across that zone of flow, and affect the path up to Mauna Loa. And even still, that pore pressure change is moving something in the order of 3 times faster than maybe several orders of magnitude faster than the actual magma is flowing itself. So magma is flowing slower than the pressure is moving through it and changing. And that's how it can adjust how much magma is flowing and how fast in certain areas. And that's how it's a tricky thing, because the magmas still don't change paths. You still don't mix the chemistry of the magma. It's just a way that you can connect them, almost like a hydraulic pressure connection, right? Rather than physical pathway connection or direct magma supply connection. There's something common that's below where that split happens, right? So, or I'm sorry, that preserves that split in chemistry is what I'm trying to say there. So interesting there, right? So you can see that as Kilauea increases there too, then Mauna Loa really slows down there. Right? And interesting that they actually put in that blue dashed line to show what it would look like with a constant East Rift Zone output, rather than it spiking up here, causing it to flatten out, right? So when the Kilauea output spikes, Mauna Loa slows down, and that naturally leads to the questions of what happens afterwards, right? And so that only goes through 2012. That was this period right in here. That was that first little bump on Mauna Loa. There's that second little bump before it flattened out. You can see that there's a third little bump, 2015 here. And if we go over to our remote GPS, I can't find that one. Let me try to find that one again here for you guys. There it is. So this is a 2015 pulse right in here. See, it came up, and it seemed like it had flattened out. That pulse, it was an initial burst right here, and then it seemed like it slowed. You can see that from 2016 on, it has been coming up, right? And I did mention a little bit of a flat spot right in here, and now that we know that a big output of magma in Kilauea, whether it's more magma into the deep rift, more magma coming out of the ground, or more magma into the summit magma chamber to the point where it's overflowing a lava lake, as was the case in 2018, early 2018, that may have led to this flattening of Mauna Loa's. And here in August, Kilauea's eruption ends. You see it picks back up again, heading upwards there, right? So that only goes to 2018. Let me advance it here to our most recent 5-year plot, taken from the USGS website here. So you see that since 2016, we've been on a slow, steady climb, right? There is the flat. And really, since 2018, after the 2018 eruption, we've been climbing at a steeper rate. We've been spreading the caldera's distance at a steeper rate than before, right? And we just showed you the graph where it showed that Mauna Loa would have a steeper rate if the East Rift Zone output went down. And so you can see that exactly that here. Interesting to think if that might be the case, might be connected, if that model does work here. Kilauea's East Rift output goes down, and here is our increased Mauna Loa rate, right? So that's interesting because when we start talking about what's happening over here, we're starting to see something happen on Kilauea in this realm over here, right? To the point where if we look at the SO2 plot as a proxy, once again, right, for our eruption rate for this 2020 eruption, it really spiked really high here, beginning in this and mid-December, we'll call it, right, mid to late December, before it dropped back down again. And so he's kind of curious, will this spike have any effect? Did it last long enough? Did it have any effect to send any signal to Mauna Loa? And if so, when would it arrive? You know, we said possibly 6 months, right, as an order of magnitude there. It's been 4 months. Is it too soon? Could we maybe be seeing the beginning of influence of Kilauea? I wouldn't go so far as to say that personally, right? But it's interesting to think about that whether there might be some relation there to behavior of Mauna Loa, behavior of Kilauea, if Kilauea can really slow down the rate. Maybe would expect it to be more flat rather than actually dipping all the way. So something else is going on Mauna Loa, would be my expectation. But maybe when all this is said and done, we come out at a flatter rate than we had before, right? Because of what Kilauea is doing. So it's all we can do at this point is look at that and try to speculate, project into the future, and really try to understand, right? Now we can see that when we look at that USGS update and it talks about how this contraction signal might be due to deflation of that shallow summit reservoir. We've seen evidence of that, right, with some of this past data and the configuration there. It could be moving possibly back into that deeper dike and out of that shallow chamber, right? That would be maybe what the USGS referred to in her tweet earlier as that deep cycling of magma, right, from shallower to deeper areas, moving from the summit reservoir down into the deeper dike area. Why? Because the flanks moved enough to allow that space to be there for that to happen, right? So that would be one possibility there of what it could actually happen, that the volcano is still filling and filling and filling, but as it spreads apart, the top keystone can kind of crumble in a little bit, right? Even as the whole bottom is lifted upward. That is a possibility, that it could be filling at a deeper level. And so we'll have to see, and we'll come back around to seeing what the USGS says with their InSAR as the last thing there, the last clue for what the interaction is between this broader inflation signal and then whatever smaller deflation or whatever contraction signal is happening at the summit, whatever that may be. We might get some light on that with the next iteration of that InSAR there. So that's just a little bit more on a connection of Kilauea and Mauna Loa. I obviously can go into a lot more detail than that, but that's enough, I think, to show those signals and enough to tease the relationships there. And of course, we'll keep watching those volcanoes for a long time to come. So we will have time to talk about this again, but we'll leave it at that point for now and take our last questions here before we wrap it up, before we hit our 2-hour mark here.
Yeah, we've got a little bit of a long one going today. There aren't many questions to end this one out. Looks like the one that I have on deck here is just pretty simple. About the lower east rift zone on Kilauea and it refilling. Just somebody's asking about what is your thoughts on the lower east rift filling as opposed to the middle and upper rift filling on Kilauea, like going on currently?
I haven't seen much data of that. I mean, it seems like that was something that was happening earlier, especially in the build up to the 2020 eruption. We saw filling signals going back to maybe June 2020, right? Especially June to December, we saw a lot of that. So it seems like there is some way for a trickle to get in there and fill it passively, per se, right? To the point you do see some of those signals. But when it came time to backflowing, that didn't seem possible, right? So that
Right.
barrier at Pu'o'o, maybe that's that semi-solid barrier that's something to do with that degas magma down in there that maybe drained out and is maybe messing with the conduit back there that was speculated to fail. You guys would have to go back and look at the research on HawaiiTracker.com. We'll cover it next week on the viscosity of magma from earthquakes there to get a little bit more of that. But they do say that there might have been some semi-solid plug of stuff that failed there, and if you have some version of that that's like a one-way valve almost, right, where stuff can trickle through it in one way, but it can't flow back towards the summit from there, because that was a limit of backflow from the summit, right? Then you might have some situation like that. And how shallow, how deep, who knows? And one thing to add, just like Mauna Loa, a lot of the time it can, you can fill in passively and then move the south flank and fill in a little more and then move the south flank and fill in a little more, and all that's fine without it having to erupt. It basically can fill that rift zone passively. Now, the eruptions are what we care about. That's a little bit different. Taking more buildup, more flank movement, more catastrophic all across the board, right?
I like this question. Back up to Mauna Loa. What do we know about? I'm going to combine two questions into this one. What do we know about summit explosive eruptions and summit lava lakes on Mauna Loa? Are they possible? Have they happened in modern history that we know of? Anything along those lines?
Yes and yes. Yeah, there have been summit explosions. We can cover that some other time. I want to say 5 discrete events, explosive events. The most recent one a few hundred years ago, leaving big solid blocks of magma that was previously had cooled underground, so no bubbles in it. Big blocks up on the rim, so explosions that lifted these big fragments out of the caldera and dropped them on the rim. So that happened 4 or 5 times. And lava lakes also have happened. It's since Western history has been here to document. Yes, I want to say maybe 3 long-lasting lava lakes that lasted more than a couple of years, kind of thing. Although usually it's shorter eruptions than that.
All right. We have a general question here from Arlie Jefferson from the donations. It's a general question: how effective are small-scale physical models and experiments in understanding volcanoes?
I think they are useful. It's just a matter of starting with a simple model and then you add some complexity more and more and more and more, right? So that that typical deformation model that we use is like a balloon under a pile of sand, and you can actually take a balloon and put it under a pile of sand and have a little bicycle pump and pump it up and watch the sand deform over the balloon and let the air out and watch the sand deform over the balloon, and that gives you a pretty good idea, right? That's just like one balloon. Now, what if you were to get a animal balloon, a long skinny one, and use one of those instead, and put it under a pile of sand on Mauna Loa, adding complexity in the shape of the balloon and the shape of the sand? You might have different kind of features from that. If you can get one that was good, and if you can evolve it enough, right, or you can take the things that you're learning and extrapolate them in the right ways, which is tricky. And that's the art of science per se, right? Is knowing how to do that appropriately.
Right.
Then you can actually gain a lot from those first order models, right? So it's interesting. A lot of times when people are doing these models that I'm presenting in this research, they're fiddling with a lot of the variables and seeing how big a difference does it make if my uncertainty in this variable, were to put it to this value, what would that look like? What about the other way? oh, it doesn't change it that much, or changes it slightly this way, slightly that way. And they might put that in the supplemental materials, for example, like all the tests they did, like the calibration tests, and why what they presented was the most optimal solution and what the range of solutions might be if it's not exactly that, because like we said, these are not unique solutions, right? Sometimes they use Monte Carlo-like approaches, and it's just something that works. It might not be the only thing that works, but they found something that works, and it works where it fits everything, and they're going to stop looking. That's it,
Right.
So
there are some really good models. Like the caldera demonstration with the balloon and like baking powder or whatever that you decide to use on that. That's one of the better ones for, especially the inflation's great, but the caldera collapse when they did it, I was like, oh, okay, now that makes total sense. That's very easy to do. The other one that immediately just jumps out in my mind was the tsunami models that are in like the Pacific
Wave
tsunami. Little wave tanks.
Mm-hmm.
I mean, it's really good to show how these essentially work at that first order, and they do a good job at what they're meant to do.
Yeah, for sure. So yeah, I think that's the basic understanding there, right? Is the understanding of how those things work, and then only then can you start adding layers of complexity, right? And we're gonna have both a blade and a sphere, and we're gonna put it in over here, and we're gonna bend it this way, and we're gonna assume it's completely planar, and I don't know. That's where it gets all tricky.
Right. Well, I believe that actually does it for a lot of our questions. I'm just going to do a double check on all these. People mentioning Bahal is still shaking down there. Yep. But yeah, that does it for most of our questions. Appreciate everybody that contributed. We do have one last donation that came across on HawaiiTracker.com. I wanted to shout out Deb B. And that does it for me. Appreciate everybody. Make sure to like, subscribe, go to HawaiiTracker.com. Check us out there. That's where we're going to be posting all of our written stuff. It really is to get the complete picture. The YouTube, we really try and get as much as we can into our YouTube live streams, but if you want the rest of the week with content, that's where we do it on HawaiiTracker.com. So with that, I pass it back to you, Phil.
Right, mahalo, Dane. Mahalo, Hawaii Tracker. And yeah, we'll be back with you guys on Tuesday next week, and we will focus more on Kilauea at that point once again, after spending more time on Mauna Loa today. So mahalo everyone who's liked, shared, supported us, contributed, donated, all the above. Mahalo Hawaii Tracker. For Dane DuPont, I'm Philip Ong. Aloha.